Okay, so one question about the exam. Question one. Trying to figure out how to address it without doing the answer here. So it's sort of, yeah, it's like 1A, how do we find isomorphism? So it's tricky. So, well, I can say something. So there are all kinds of isomorphisms for between groups, subgroups of various groups. And so I think maybe the sticking point here would be how do you, if you know you have the right answer. I'm hoping, tell me if you guys have looked at this problem. Has anyone looked at this problem? Okay. So if you know do you guys know that you have the right answer? Do you know what the answer is? What the group is? What the subgroup is? Or what do you think you know? You feel, you've got a feeling. Okay, you've got a good idea. All right, the first thing to do now, okay, if it's only a good idea, and it's not like, oh, I know this is the right answer. How do we like reassure ourselves that it's probably the right answer? You can count the number of elements, right? That's the first thing. So it asks whether or not, or it asks find a subgroup H of SL2 FP for H is isomorphic FP with that additive. FP is a field. The first thing to do is find a subgroup that has the right number of elements. Find like H, so H has P elements. So I listed several groups last time that you could consider. I said, okay, so one thing you can consider from that list would be like consider this consider that group, right? Alpha is in FP, but what do I need to assume about alpha? If I thought of this group. That it has an inverse. So what is alpha? FP is a field. So which elements of a field have an inverse? All but zero, right? So alpha is non-zero. Okay, so I could consider this. This is a subgroup of SL2. I mean, if I take the determinant, it's alpha times alpha inverse. So that's right. So this is this, and you can easily see it's if you multiply two, it's closed under multiplication. All of that. This is a subgroup. However, if I count the number of elements, how many elements do I get? So if I call this like K, the number of elements in here is what? P minus 1. Right, P minus 1, because I'm taking away 0. So I go P minus 1. There are P elements in FP, and I just don't want 0. Whereas the number of elements in this group is P. It's all of them. It's the additive. So this doesn't work. I'm taking through a process of, I can't give you the answer, but I'm trying to say, okay, here's something you can check. See if you get the right number of elements. This one's not going to be good. So it's something else. Once you kind of feel like, oh, okay, it must be this. And really look at the groups I talked about last time. It's one of them. Give you a big hint there. So, once you know that, then you need the isomorphism, right? And you need to actually talk about the isomorphism. And so, so to prove this fact, once you have the right group, you want to give yourself all you need to do is give yourself a map. So you should give yourself some map, probably from FP to H. Bijective. So you want to prove it's bijective, which would probably be by definition your subgroup H. And then show some homomorphism. You just show that, if I take this, remember the operation in SL2 is matrix multiplication, but we're dealing with the addition operation. So, I mean, I can't, as I said, I can't really give you the answer here, but I can say there are a lot of isomorphisms that you can consider like this. So one, I remember I was talking to Gail about Mobius transformations. These transformations. No idea why my wife hasn't left me yet, but talk about Mobius. Here's a Mobius transformation. It's a map, right? I mean, you have to make sure that Z is not like D over C or something, negative D over C. This gives you a map. And this is, so if I consider all of these, where CZ 0 as a expression. This is actually a group. And here, let's assume, doesn't matter. I mean, let's assume A, B, C, and D are real. It's a group. Under composition. Compose two of these functions. So in other words, if I take like one that looks like F and I take another that looks like G, and I take F equals with G, this is also going to be. It's not completely obvious, but you can work it out. It turns out, right, this group is isomorphic to a group called PSL. I guess what I would say is you can prove this. So I'm just trying to say, how do you go about proving something like this? You need to furnish yourself with a map and show it's a homomorphism. So there is a map here. So I take a matrix A, B, C, D, map it here. And you can check the psi of to make, that psi. I might have the rough, I don't know if I have the exact right order here, so I might have to switch B and C. So I'm just trying to say, okay, how do you prove something? So this would be a map then. So this is a little more subtle than the one that I'm giving you the problem, because this is one where this is a map from SL2, and it would actually have a kernel, and the kernel would be negative, the negative times diagonal. But then you use the first isomorphism here to show that. I guess we also need, I should have said, we also want AC. There's another question. Yeah.
For psi that you defined up there, isn't the map from H to F? What E of A times B is equal to 3 of A plus 2 of B?
This one here?
Yeah, like when
Here. Well, I asked for you to show an isomorphism here. So it doesn't matter which way you can go for, it's an isomorph, not a homomorph. So there should be a homomorphism one way and a homomorphism inverse. That's also, but you choose. You go whatever way you want to go. Like it's whatever you want to do, right? Life is, freedom is great. And so, right, go from H to FB if you want. The point is that I think it'll be more natural to go this way, because you'll write down your group H and you'll see elements of your field, and then you can say, oh, how can I take an element of my field and get an element of H? Well, I'll just take this element of my field and write down this element of H. That will give me. You can go the other way if it's easier. But the operations are correct. The operation in FB is addition. Operation in H is matrix multiplication. Good. Okay, give it a try. And if you're like really struggling, send me some hate mail, email, whatever. And I'll react. Yeah.
Is there like a cutoff that you can't ask any more questions at this point?
Yeah, after the due date is probably. Well, you can actually, no, that's not a cutoff. You can ask as many questions after the due date. But no, I do have this Calc 3 that I'm coordinating, which is keeping me pretty busy. So I've got some review sections for them, and I've got to orchestrate the massive. So painful. Talk about breaking out the burden or something. Like you need to feel the question. Like there's a lot of unpleasant feelings. What can you do? 300 students can make everyone happy. or even half of it. Anyway, all right, sorry. I'm off topic. Problem 2. Let's take a look. And you guys should say, look, if there's something you're shy in email and you want to say something, say something. I'll try to address it now. Copy that. All right, so we've got this problem here. And I guess what I was thinking to talk about here is just to make sure. Okay, so what's the hint for A? I mean, I guess the hint for A is to consider the kernel. That's sort of my hint. Just ask yourself a little bit about the kernel. For example, can it empty? Or not empty. 0, does it have something non-zero? Something like that. If you ask that question and you feel good about your answer, that might lead you to some question. So, another thing you could ask is, so this is one thing to consider that might be helpful for you. Another thing to consider, which will be probably maybe even more helpful, is consider this property. If this is not 0, if a transformation or operator is not 0, there has to be a vector somewhere in this vector space that when you hit that vector with your transformation, you don't get 0. In other words, if I have a map S from B to W, and I say S is not equal to 0, well then there is a B and B for which S of B is not 0. I mean, if every single element was sent to 0, then it would be 0. So I would apply that to this problem. If you even find a particular V that satisfies that, that will help you, I think, a lot. Okay. There's a big, that's actually a pretty big hint. So hopefully that. And then for this, so we did talk a little bit about this in lecture, but I thought I would, just remind you what it means. So here, maybe I should have written operator. Transformation is the same thing, but you have to specify the domain range. But I've done that here. Operators means a linear map from some vector space to itself. Okay. So what does it mean, a matrix of a linear transformation? You guys remember? Okay. Well, and in particular, a linear operator. Linear transformations, you need 2 bases. Linear operators, you just need 1. So that makes them slightly easier to deal with. Let's say I have a mission with respect to basis B. Here I have a basis B1. Okay, let's give an example. It's too abstract. I thought of an example, but I think it's too boring. best examples are infinite dimensions. All right. Well, let's just do something. Let's let V equal polynomials of degree. Coefficients in R. It's a real vector space. Add polynomials of degree 3, you get a polynomial. I mean, degree less than or equal. Subtract them. Multiply by a real number, it'll stay in that set. All the usual rules apply. Now let's give ourselves a linear operator. So let's consider x squared. So this is an operator. It operates on polynomials. I mean, it's an operator on like twice differentiable functions. Take twice differentiable here. Just hit it with that operator. And if you wanted to say find the kernel, you could be asking, can I solve this? So, but we'll just think of it as an operator, and we'll just restrict the set of functions that we're considering to the set of functions that live in V. Now we want to write this as a matrix. It's like Heisenberg. I guess this is who's the fifth? You're the Heisenberg, right? Come on. Kale. I mean, there were two approaches in quantum mechanics when it started out. One was like the Schrödinger approach, I think, and that was the Heisenberg approach. Matrix versus the different. Rock. Rock. This is the Dirac approach. Sounds wrong, but okay. I agree.
But it is the Schrödinger equation, but you use matrix.
Okay, good. I feel good. I mean, he does have the Dirac delta, so it must be good. All right, so let's do this. So we need a basis. We need a basis. But there's an obvious basis for this. What is it? Oh, that's really nice. All my years. What's the basis? Yeah, 10. Unit vectors. What's okay? I'll give one unit. I don't know what else you mean. What are the other? One is a polynomial of degree less than or equal to 3. And it is a unit, so I'll start with that one. And I agree that should be in line. But I don't want to think of it as a unit. So you're thinking of like the standard basis vectors. If I had R, so what's the dimension of this? This should be dimension 4. So yeah, if I had, I was thinking of it as column vectors to be fine, but I'm not. This is a polynomial. So what are 1 is 1. X squared. Oh, we're on a roll. X cubed. All right, you guys are the best. Okay, good. Right. So we got V. This is our basis. Now, I think that there's sort of a convention, and I'm not going to be sensitive at all to the answer on this convention. It's not important to me at all. But it's sort of a convention as to whether you consider this as a column or a row. whether your isomorphisms you're making it with columns or rows, in other words. But I'm going to just consider so let's call this operator. I need to call this operator something. So let's call it T. I want to say T of VI is going to equal the sum of AIJ VJ. Now, again, I guess I'm going to. Here I'm choosing a convention, and I'm not, I'd have to work out, which convention it is. But it does, as I said, it doesn't matter. It's either this or it's transpose. So what I'm saying is the matrix of transformation is going to be this guy. What's transpose? 4, because I've got a 4-dimensional space. But in general, it's whatever the dimension of your space. Again, you may be switching I and J here. It's okay to do either. It's just a question of whether you're doing rows or columns when you're doing this. So here we just calculate. So what is T of R1? 1 is 1, right? 1 times 1 is 1. So this will give us our first row of our matrix. This is 1 times 1 plus 0 times x plus 0 times x squared plus 0 times x squared. This gives us, I kind of feel like I should take the transpose between columns. It's okay. I'm just going to stick with this. T of 0, T of x, pardon me, is -2 plus 1. Can agree?
Where you're getting that.
An x. X. Derivative of x is 1, we get -2. Second derivative of x is 0. Yep. And then I've got a plus, if I want, let's just write it out here. Here. -2. Oops. These are the coefficients, not the actual base. If I put in an x squared here, x squared, right this way. Okay, so I'll give 2. Second derivative of x squared is 2 minus 2 4x plus x squared plus 0 times x. 2 minus 4, 1. Finally, cube x cubed will give me 0 times 1 plus 6x. Zero, 6. This matrix, so then if I think of these guys as being, as Tim was saying, the standard basis vectors. Identify these with standard basis vectors, which are row vectors in R4, then this operation T operating on this will be the same as multiplying that row by this matrix. So this is sort of the row vector. Otherwise, I take transpose and I make it. That's how you find the matrix. But you can look in 4.2. It's a computation. It shouldn't be feared. Plug in your base vectors. be scared, guys. I think this one, that one's kind of straightforward, actually. It shouldn't be too bad. It's also not too bad. Nice. Wrote down a couple of things. But one big hint is just to make sure you guys know what's going on, like what this is. I think you all know because I talked about it so much. So I do talk a lot. So. So I think the thing that will help you with this problem the most is to identify what is this. But not just in general, but what is this? So what is -3? It is a quadratic number field, and Jillian Carson, you got it. So it's a quadratic number field. But what is number 3? -3. -3 is in our new way of thinking. That's fine, fair enough. But that's not relevant at all. So what is in terms of quadratic number fields? This is our lowercase d. What do we care about with d? Huh? I'm looking for this. We consider rings of integers of q square root of d, and we classified rings of integers based on what with respect to d? True. We did do that. That was okay. Fair point. Not what I was after, but it is a fair point and it's more relevant than prime. So let's say, so this tells us that we have an imaginary number field. Imaginary, and you do want that. Good. What else? Rings of integers. You mean it's a PID? Yeah. Well, the answer is yes, but that's not what I'm asking, but it's true. I can't argue with it, and I don't think we proved it or even came close to proving it, but it's true. Not yet. Not that. What did we ask about in imaginary number fields? Rings of integers. What have we been doing, guys, for the last 3 days, 3 lectures? That's been boring you guys here. What is the okay, but what did the lattice look like? The ring of integers. Okay, one was a rectangular lattice, right? And were they all rectangular? No. There was another one that was sort of like a rectangular lattice, and you shifted it and moved it, right? So it looked like you had like this isosceles triangle. What told us which one we were in? What told us what case we were in? Mod 4. Oh, thank you. What is this congruent to mod 4? I'll take some of this name. 1. What is the lattice look rectangular, box lattice, or the other?
The other one. The other one.
And remember, in that other lattice, there was this new thing called new. I heard that like they didn't do Omicron, they didn't call it new, which was like the next letter they were supposed to use because they were worried about saying the new variant. I think it was great. And all right, and this, what was this? This is 1/2, 1 delta. This is the form. Here, delta is the square root of 3. What is this guy? Where is this? You've seen this, right? You've seen this all day long. You've seen this since you were in the cradle, I think. Alive. Part of this American tradition to torture children with this. Right? Never understood it. But it's true. Now 3 students asked me. Honestly, the new expression I learned this year. I want us to memorize the unit circle. Understand. I heard it twice though. How do you memorize? Now I realize, well, they mean like the value, the trigonometric values of like sine and cosine for like 6 different values. Oops. All right, so this is where? This is right. Pi over 3. Isosceles triangle. The hexagonal lattice. R is as a lattice is the hexagonal lattice. It's this beautiful lattice that, as I say, always it's on the upper floors. This is the lattice. And unlike other, the group of units, if you look back in the notes, pretty special in this case, in the case where you've got, the Gaussian integers. These are actually called Eisenstein integers, I believe. Some Eisenstein, some German integers. I forgot. Yes, it's but if you look at in the text, there's the group of units in this case, of course, is just these 6 elements. So when I'm talking about expressions like this, I'm saying, you have 6 opportunities here, not just plus or minus 1, to kind of multiply by your unit. When you do that, what are you going to get based on what we know about multiplication in complex numbers? If you multiply by a unit vector in complex numbers, what does it do? Unit vector. It rotates. So this multiplication by alpha will be a rotation by, a multiple of pi over 3. So that's behind this sort of thing here. A rotation, we're going to have a translation. And this would be true in any number field, but in this case, it's kind of, you've got the maximal number of possible rotations that you have for a quadratic. So you get kind of an interesting. So this, hopefully that'll help you a little bit in thinking about what you're doing here. But these problems are pretty, I think, straightforward just from the perspective of just go ahead and do it. This isn't, I'm not asking you to come up with any super new idea. One other thing to do or to notice is what is this? So I'm saying, okay, here we have things that look like rotations by multiple 5 or 3 and translations. Let's add something new in. Let's possibly take a conjugate of RC. But what does conjugation do? Well, I have A plus BI. What is the conjugate of A plus BI? A minus BI, right? So it's going to reflect across the x-axis. So here I'm saying, okay, add in the reflection. How's that changed? That helps. Okay. Address B?
Yeah.
Oh, B or B. I'm like, this B or D? So, yeah. So I'm saying, so what happens here? Think of this as a composition of operations. So first I take my element Z and then I multiply it by alpha. That's going to rotate it. And I translate it. That's going to, so I'll get a rotation and then a translation. If I do the same kind of thing here, what do I do? I take Z. First now, instead of multiplying, I'll hit it with Z bar. That reflects. Then I'll hit with alpha. So I'll reflect, rotate, and then I'll translate. So this is a composition of things. All isometries. So probably B does not change as far as the answer goes. Because I have a composition of isometries. I don't know, you should think about A, probably C. But I'm adding these. So I'm not everything is of this form. I'm saying take all of these and then put these in as well. Of course, if I just considered these, it would not be close, right? I could conjugate twice. But so I'm just adding these. And then C is a question about state. This is kind of I think the hardest part, right? Is understanding what the stabilizer groups are at various points in the plan. Those are the set of symmetries that will keep that point where it is. Of course, if I just took the origin, for example, these rotations in this group, they fix it. So I get at least some stabilizer group there. But I'll let you guys think a little bit about that. All right. Second. All right. So what about 4? So let me just say something about, so 5, I think actually, so this is a little bit of a challenge. I want to see what people say here. See how far people get. This should be pretty quick. So this, just look at the last lecture and you should be able to kind of figure that out pretty quickly. I'm not going to spend any more time on 5, but let's look at 4, and I'll at the very least, I'll give you like a way of completely cheating here if you want. Which is fine. If you want to cheat this way, I will give you full credit. So there, what I mean by that is that there is a theorem that will tell you this is true. You have to actually repeat the proof of the theorem though. In this case, you can't just say, "Hey, here's a theorem that says it's true that we didn't cover in class, so therefore it's true." like that's see Wikipedia does not get you 20 points. But although back in prime COVID time, that was sort of the way we're coming out, right? Yeah.
When you say like you gotta state it, you could be like, by this theorem which says.
Oh, no, you have to prove this. Come
You
on.
can
You
say
still like,
theorem, and then you
I'm
say
giving,
proof.
the cheat is that I'm telling you that if you really struggled with this, you could go find out, look at a proof of this. But then you would have to take that proof and use it in this case and show that proof in this. I want to see the proof.
So the proof is more general.
General. Probably, I don't know if it's more hard or not. And there's actually many proofs.
So I don't.
It's not, no, yeah. This is like total corruption. Okay, so, like, listen. I want you to understand. I want to see that you understand it. So don't copy it, and it should be adapted to this particular problem. I doubt that you'll find anything anywhere that just does it for 2 by 2. Probably you will, but I don't know of anything like that. That would seem like a very silly thing. Okay, so there's something called Smith normal form. And it says if I have it's not, it's any matrix, any m by n matrix. I have some m by n matrix. Entries in PID. That's whatever this is. Entries in a PID. Then it says, okay, you can get, then there's some P and Q, so that PAQ has this particular Smith normal form. Like alpha 1, some diagonal guys, up to alpha K, and then 0 down here, 0 over here, 0 here. And then alpha 1 divides, alpha 2 divides. This is Smith normal form. So I'm asking you to say, okay, apply Smith, show that you can get something in Smith normal form when it's a 2 by 2. So if you look at the proof of Smith normal form, you should be guided to some degree on how you could do this. There's like, you'll be like, oh, okay, this is, but it's not exactly like the easiest way, I would say. I would say you're gonna have to read some, depending on the source. Maybe there's some that are elementary, but like they're all elementary. They're not. They're all. You can read any of them and feel okay. But here's what I want to say. I'm gonna, yeah. Let's do it for an example, and then maybe instead of looking at the proof, instead of cheating, you'll just do it maybe a different way. Let's say I had this. Let's say I had this. I want to find my. You get it. This is almost of this form, right? But I don't have this divides this. So now, okay, so now I want to hear from you guys. So I've got like 4 minutes. Let's hear. What do you guys say? What do you think? Let's say you want to find a P and a Q. What do you think? I'm not, by the way, I'm not conjugating. PQ is not P inverse. Q is any 2 by 2 matrix you want. That's inverted. What if I didn't have a Q? I mean, obviously I couldn't get this, but what if I didn't have a Q? I want to multiply a matrix on the left by something that's invertible. Have you ever done that? Have you ever like talked about like multiplying by invertible matrices on the left? An interpretation we had for a sequence of doing things like that. What? Yeah. What were those? What was that process? What kind of operations were we performing? Row operations. Very good. Row operations. Row operations. We got invertible matrices. Now, If you multiply on the left by an elementary matrix, you have a row operation. If you multiply on the right by an elementary matrix, guess what you have? A column operation. Now, we are, however, not in the world of row echelon form. We cannot put things in row echelon because we are not in a field. R is not a field. R is a PID. So there are some row operations that are verboten, as they say in Deutschland. Right. Yep. Good. Okay. So what are they? What can't you do? What are you not allowed to do? Identity. What do you have in a ring that you, or what did you have in a field that you don't have in a ring? Inverses. So one thing we did was we were able to multiply by whatever number we wanted, like a row by any number we wanted. Particularly, we were able to like clear things out, to build a, divide by number. We can't do that. We can still multiply, but we can only multiply by unit. If we're gonna make it through. And that is basically it. That's the only limitation. So what I would say is do some operations. Let me do it real quick. So I noticed that 3 minus 2 equals 1. Don't tell me how, don't ask how I noticed this amazing thing, but I did notice it. So I can do a row operation where I add the second negative of the second row to the first row, and I get that. Now I can do a column operation. Where I add the second column to the first column. Notice I get 1, 2, negative 2, 2. Now all of a sudden, what have I accomplished? 3 just became 1. 1 divides everything. Life is good. Now I can use good old row operations. Multiply, so I can add a multiple, any multiple, if I'm in a ring, any multiple coming from the ring, to another column. That's still invertible. So I can add 2 times negative 2 times the first row to the second row, keeping the first row the same. That is still permissible. I'll get 0, I'll get 6 here. Now I've got this annoying negative 2 here, but and you would say I'm stuck because I want to do operations here, and I can't divide by 6, but I can do column operations. I can't do row operations to get rid of this, but I can do column operations to get rid of that. I'll do that. I just multiply by 2, the first column by 2, and add it to the second column. One does divide. So I'm just saying, if you could probably prove this without too much work by using these just row and column operations. And some of the proofs of Smith-Norman form are exactly. Yes.
So what we ended up with, would that be like
No, okay, so we did the procedure to get this into the form. But now when you do, okay, so good question, Joe. So like the idea is whenever you do one of these operations, you're multiplying by a particular elementary matrix, either on the left or right. So you need to, if you're to do this properly, you need to write down what those operations are and then write that as a matrix. So in other words, this is going to equal, the first thing we did was a row operation. So this is going to equal 1 minus 1. Right. So, and each time we do one of these operations, we're multiplying by a particular matrix. But you don't if you're going to prove it, you don't actually need to record that. You should say that. Each time I do this, we're multiplying by a vertical matrix. But, you know, I'm not asking you to actually perform the algorithm and give me the matrices. I want you to show that they exist. Okay, guys. Yeah, I'll, you know, look at my email this weekend. So let me know if you're further questions.
I need to look at that one.
Oh, thank you.
Yeah,
I knew I was actually going to ask you.